Alright, let's get to another important theorem as we start the third video of lesson 2.3. We finished the last video with the remainder theorem. Now we're going to talk about the factor theorem. They're kind of related. Given f is a polynomial. Now notice how this is written. By the way, IFF is if and only if. F of c equals 0 if and only if x plus c is a factor of f. That means I can say if f of c is equal to 0, then x plus c is a factor of f, or I can reverse it. If x plus c is a factor of f, then f of c is equal to 0. So it's kind of a nice notation there. And what this is telling me is exactly what I need to determine if I have factors. That's what this first example is. If the remainder is 0, because remember from the remainder theorem, this is the remainder. So use the factor theorem to determine if the given polynomials are factors. So I'm going to find f of, my c value here is 6. Right? So I'm going to use synthetic substitution because I think that's more efficient. Fortunately, my polynomials in descending order, no missing terms, no placeholders. And in the pocket goes a 6. So that's a 2, that's 12, synthetic division, negative 1, that's negative 6. That's, that's a 4, that's 24. That's negative 1, and that guy right there is negative 6, which gives me a remainder of 0. So now I have one factor of this, and I could take this guy, my what's left, the quotient here. Sometimes this is called the depressed polynomial. 2x to the third minus 1x squared plus 4x minus 1. See if I could factor that. It would be a little tricky because it's degree 3, but we'll learn some things to help us with that later on. But in this case, because I get a 0 here, and because this says if it's a 0, it's a factor, then I know, yes, x minus 6 is a factor. Now, let's do the same thing over here with x plus 3. In this case, c would be negative 3, because it has to be in the form x minus c. So 2, negative 13, 10, negative 25, and 6. A little space there, put the negative 3 in. So that's 2, that's negative 6, that's negative 19. That's 57, doesn't look good. That's 67. Ooh, that'd be negative 201. That's negative 226. It does not look good here. So what is that? 678, so 684, I hope. There's my remainder. Since that's not 0, it is not a factor. So x plus 3, no. X plus 3 is not a factor. Alright. And let's go over to here, where we are going to try to factor the polynomial given a 0. Now, if you have a 0, remember how this works. If this guy here is my 0, call it c, then that means that f of c is equal to 0. It means that x minus c is a factor, if I can spell. And it also means, as it turns out, c is a solution of f of x equal to 0, because it says 0 of the function f. So I'm going to use synthetic substitution. I'm going to go 2, 7, negative 14, negative 40. Now, if that is a 0, that means if I use synthetic substitution, my remainder better be 0. 2, negative 8, negative 1, 4, negative 10, positive 40, 0, just like we'd hoped. Now, let's go to this guy here. This is my quotient, and as I mentioned before, it's sometimes called the depressed polynomial. I don't know why it's depressed, must be married. So this is constant, this is x to the first, this is x squared. My quotient is 2x squared minus x minus 10. What that tells me is f of x is equal to x plus 4, it's a factor, times this quotient here, 2x squared minus x minus 10. That means I'm going to see if I can factor this guy, and since it's a quadratic, with a little luck I'll be able to use my factoring skills and see if this will break down into maybe a couple of binomials here. I'll try a 2x and an x, probably a 5 and a 2. And I need a minus 1 in the middle, so minus here, plus here, and I have completely factored my polynomial f. There's my answer that's underlined. Now, with this in mind, notice that this example leads to this example because these are exactly the same polynomials. So it says solve this equation. Well, to solve an equation like this polynomial equation, I would try to factor. I just did that. So this guy is x plus 4 times 2x minus 5 times x plus 2, and that's equal to 0. So that means either this is 0, or this is 0. See how they're all related? Nice. So I said each one of the factors equal to 0, and I solve. I would subtract 4. There's one solution. I would add 5 divided by 2. So there's another solution. That would be 5 halves. I would subtract 2 from both sides, and I get x equals negative 2. So my solution set would include negative 4, negative 2, and 5 halves, putting them in order from least to greatest. All right, now I'm going to reverse it. In this problem, I was finding solutions to the equation, which is a little bit like finding the zeros of a function, given the function, because I already know how it factored. But now this time I'm going to reverse it. I'm going to start with the zeros, and I'm going to come up with a polynomial f of degree 3. Well, that makes sense. There are 3 zeros, degree 3. That kind of matches up. So what you have to think of is, if these are zeros, these are also the c values for these factors. So my function f of x would be equal to x minus 1/3, x minus the square root of 3, x minus a negative or plus the square root of 3. And they would want you to multiply that out together. It looks a little messy with the radicals and the fractions, but these guys are conjugates, so I could multiply those, and that would give me x squared, looks like minus 3. And then I would use FOIL, and I have x to the 3rd power minus 1/3 x squared, trying to keep this in order, minus 3x plus 1. Now there's nothing really wrong with this answer. That would be a polynomial that would have that. But you know, to avoid the fraction, if you multiply through by 3, you could write another version of f of x, just that it wouldn't have any fractions. So if I multiply through by 3 on the right side, it just looks a little bit cooler to avoid that fraction in that problem. And that is that polynomial. So given the polynomial, we can find zeros. Given the zeros, we can find the polynomial.